In this video, we'll talk about how we can prove that a bunch of statements are equivalent. So we'll have a chain of if and only if statements that we need to show. All right, so I want to begin with a proposition which says that P implies Q and Q implies R. Okay, so if, and I have an implication here, so it means if P implies Q and Q implies R, then P implies R. So if that sounds kind of familiar, that's good. This is something called the transitive law, and this is a tautology. And I'm going to give a picture as an intuitive reason for this. So if P implies Q would mean that, well, if P happens, I'll denote that with a circle. And P implies Q would mean if P happens, then Q definitely happens. So the P circle has to be inside of the Q circle. And Q implies R would mean, well, if Q happens, then R has to happen. So the Q circle is inside of a circle that I denote R. Well, that means that if I'm in the P circle, then I'm definitely in the R circle. In other words, if P happens, then R has to happen. Okay, so my goal in this video is to show that something like this is going to be true. We'll do an example of this. So P1, if and only if, P2, if and only if, P3. Keep going if and only if Pn, where the number of these propositions, the number of things in this chain is greater than or equal to 3. Because if I just had 2 of them, it's a simple if and only if, but now I'm going to have a bigger chain. So when this is true, we say that the following are equivalent. The propositions P1, P2, P3, comma, dot, 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 up until the last one, we say that those are all equivalent if we have this chain of if and only ifs. So how can we prove this? So I'm going to use a picture here to indicate my strategy. What I'm going to try to do is show that one proposition P1 implies the next one P2, and that implies P3, and that one will imply P4, and this will imply some other one. And if I keep going like this, something will imply Pn, and then Pn will cycle back and imply the first proposition. And this will actually mean that these are if and only if arrows. So even though I'm drawing them in one direction, I can actually go the other way around as well. So why is that? So as an example, like why is it true that P1 if and only if P3? Why would that be the case? Well, clearly I can see that if I'm starting at P1, that implies P2, and that in turn implies P3. So by the transitive law, that means that P1 implies P3. If I'm starting at P1, I can get to P3. But why can I go the other way around, start at P3 and get to P1? Well, if I keep going along the circle, P3 implies P4. That implies something else. And if I keep going like this, keep going like this, keep going like this, eventually I'll get to P1. So if I start at P3, I can indeed get to P1, which means I do have this biconditional. It works both ways. So to prove this chain, all I need to do is establish one circle like this. I'm going to show that P1 implies P2, and that implies P3. And if I keep going like this, this will imply Pn, my last statement, and that'll cycle back and imply the first one. So let's do an example where we do this. I want to let n be an integer and prove the following are equivalent. The first statement says 5n plus 4 is even. Then I have n squared is even, and then I have n minus 3 is odd. I want to prove all of those are actually equivalent. Okay, so I'm going to break this up into parts. I have to show various implications. So first, I'm going to prove, well, I'm going to start with the simplest looking one out of these. And I think the simplest is this one, because that's the one where I think it's going to be easiest to isolate the n and get it by itself. So I'm going to start with the third thing, and maybe I'll show that that implies number 2. Okay. And ordinarily I would do scratch work to begin this process, but because there are going to be so many things I'm going to have to prove in this video, let's dive right into the proof to save a bit of time. Already it's going to be a bit long for us to do this. Okay, so I'm going to assume 3 is true, which means I can start my proof by letting n minus 3 be odd. Let n minus 3 be odd. That's what I get to assume is true. Then I write down the definition of what it means. So this means there exists k which is an integer. There exists k, which is an integer, such that n minus 3 equals 2k plus 1. That's what it means for this number to be odd. Okay, my goal is to show 2 here. I'm trying to show n squared is even. So let's start our manipulations. So then if I isolate n here, we get n equals 2k plus 4 if I add the 3 over. Now I think I'm ready to square it. So this implies that n squared will be equal to the quantity 2k plus 4 getting squared. If we distribute that out, I get 4 times k squared plus 16k plus 16. I'm trying to show this is even, which means I'm trying to show that it'll end up equaling 2 times some integer, which means I'd love to be able to factor a 2 out of all of this. And I can. So let's go ahead and do that. Let's factor a 2 out of all of that. So that'll give me 2 times k squared plus 8k plus 8. And because k is an integer, and in the parentheses we're just multiplying and adding integers together, that's going to be an integer. So let's relabel it. I'm going to let this, well, I can't call it k again because I already have a k in the problem. So maybe I'll call this k2. Let's let k2 be equal to 2k squared plus 8k plus 8. So that is an element of z, meaning it's an integer. Again, because I'm just multiplying and adding integers together to get this number. Okay, so now we can restate what n squared ends up equaling using this relabeling. So then n squared is equal to 2 times the thing in the parentheses, which we just called k2, where k2 itself is an integer. But that's the definition of what it means for this thing to be even. It's 2 times an integer. So thus we can say n squared is even. N squared is even. Okay, so we've just proved that 3 implies 2. So let's keep this going. Now I'm going to start with proposition 2 and show that that implies the first one is true. Okay, I don't want to just go back to 3 again because I want to make a chain. And to continue the chain, I have to go to 1 next. Okay, so now I'm assuming 2 is true. So I'm assuming this, n squared is even. So I'm going to let n squared be even. And I want to show that 1 is true then, that 5n plus 4 is even. And now here's where I'm going to use a previous result. We've shown previously that n squared is even. N squared is even if and only if n is even. We showed that in the last video. N squared is even if and only if n is even. That was one of our corollaries from the last video. Which means I now get to use that in proofs if I want to, if I need it, if it's helpful to me. Okay, so because I'm assuming n squared is even, this previously proved fact tells me, well, that means n has got to be even. Okay. So this means by the previous result, this result right here, this implies that n is even. And now we are ready to state the definition of what that means. So that means there exists, well, I've already used a k in the last part, so maybe I'll use a different variable. Because I don't want to reuse variables. Let's let this one be L. There exists an L, which is an integer, such that n equals 2 times L, because n is even. Now I think I'm ready for my manipulations, my algebra. So I'm trying to show something about 5n plus 4. So this means that 5n plus 4, I can now sub in, will be equal to 5 times 2l plus 4, which is 10l plus 4. I'm really hoping this is going to be even, so I want to be able to factor a 2 out of this. and I can. So I get 2 times 5L plus 2. And the thing in the parentheses is an integer because L is an integer and we're just multiplying and adding integers together. So let's relabel it. I'm going to let it be L2 because I already have an L in the problem. Let L2 be equal to 5L plus 2. And this is an integer. So now I can restate what 5n plus 4 equals using this relabeling. So then this means 5n plus 4 is equal to this thing here, which is 2 times L2, comma, where L2 is an integer. So this is the definition, though, of what it means for 5n plus 4 to be even. So thus, this means 5n plus 4 is indeed even. Okay, awesome. So that has demonstrated this implication. So now we've shown that the second proposition implies the first one. What's left to do is show that the first one cycles back and implies the third one, and that'll complete the chain and show that these 3 statements are actually equivalent, and that these are all if and only if arrows then. Okay, so let's do that on the next page. So we need to prove that the first thing implies the third thing. All right. So, okay, the first thing, if I'm assuming that's true, we'd be assuming 5n plus 4 is even. Let's try a direct proof and see why that becomes a bit hard. So I'm going to just write some scratch work here. If 5n plus 4 is even, that means 5n plus 4 equals 2k. And if I'm trying to prove the third thing, which is saying n minus 3 is odd, I'll probably have to isolate n. So if I try to isolate n, I'll get n, so let's see, I have to subtract 4, I'll get 2k minus 4, and divide the 5, divided by 5. But if I look at this fraction, it's unclear if this is even going to be an integer at this point. Unclear if this is even if it's an integer or not. We're not sure. So I'm going to put a sad face about that. Unclear if it's an integer or not. So it's going to be really hard for us to establish if I look at that and I subtract 3, that that's going to be odd. So that's what's making me think maybe a direct proof is not the best way to go. So let's try the contrapositive. So in a contrapositive, I would assume that the conclusion, which is 3, is false. I would assume this conclusion is false. So I'm going to assume that if n minus 3 is even, then the hypothesis is false. So part 1 that I'm assuming, start off with, I'm assuming I'm going to have that that's false. 5n plus 4 is odd. And then 5n plus 4 is odd. So that's my contrapositive. So let's try to show this instead. Okay, so I get to assume the if part is true. So what that means is, n is an integer such that n minus 3 is even. So let's get into the proof. So I start by writing down what it is that I know. And I know that n minus 3 is even. That's what I get to assume is true. And then I write down, well, what is the definition of what that means? If n minus 3 is even, that means there exists some integer, I'm going to call it j. Exists some integer, I'm going to call it j, such that n minus 3 equals 2j. Okay. So now I'm going to try to do some manipulations because I'm trying to show ultimately that 5n plus 4 is odd. Let's try to do some manipulations. So maybe I will isolate the n here. N equals 2j plus 3. So now let's start to write 5n plus 4. So my 5n plus 4 will be equal to 5 times 2j plus 3, because that's what n is, plus this other, plus this 4 that I have here. So I've just plugged in for the n. N is 2j plus 3. And if I simplify this, let's see, if I distribute 5, I get 10j plus 15 plus 4, which is 10j plus 19. And I want to show that this is odd. And to show that's odd, I need to show that it equals 2 times some integer plus 1. But I don't have a plus 1, I have a 19. So what I can do is I can split up the 19 and write it as 10j and then plus 1 to get that plus 1 there. And if I split the 19, well, I also need an 18 there. So 18 plus 1, 18 plus 1 is the same thing as 19. And now if I take these first two terms, I can factor a 2 out of them. So if I factor a 2 out, I get 2 times 5j plus 9, and then plus that 1 out there that I need. Okay, so that's good, because this thing in the parentheses is going to be an integer, so I'm going to relabel it. I'm going to let this thing be j2, because I already have a j in the problem. I'm going to let that be the 5j plus 9, so that is an element of z. I'm relabeling it. So now I get to restate what my 5n plus 4 equals. It ended up equaling this whole thing at the end. So my 5n plus 4 is equal to this thing in the end, which is 2 times the thing in the parentheses, which we just called j2. 2 times j2 and then plus that 1, where j2 is an integer. So this whole thing was an integer. But that just means 5n plus 4, because it looks like 2 times an integer plus 1. That means 5n plus 4 is odd. 5n plus 4 is odd. That is the conclusion that I needed to reach. So in other words, at this point, we've demonstrated that this contrapositive is true, which is what we needed for this third implication. So at this point, I've shown that 1 does indeed imply 3, even though I needed the contrapositive for that, which is totally fine. So therefore, these 3 statements are indeed equivalent. And that completes the proof. So I'll put my symbol to indicate that I am done with the proof.